Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to basically explore the habitable zone of planets, but also habitable zones around variable stars and what happens to them as the star actually varies in output. It gets brighter, it gets dimmer. What does that mean for any planets that are actually orbiting around that particular star? So before we go any further, if you haven't come across what a habitable zone actually is, it refers to the distance from a star. So we've got a planet and it's the distance from that star where you'd get liquid water. So that would be present there. Now obviously Earth is in the habitable zone around the sun. And when we're looking for exoplanets or planets around other stars that might have the potential to have life or support life, then the habitable zone is an important thing to calculate. And if we can find planets in the habitable zone, then that's basically ideal really. So that's kind of what it refers to. We need to have kind of liquid water there. It's the zone where we would expect life to be able to thrive and survive. So we've got the habitable zone, which is the green section there, and the planet is orbiting in that. Now if the planet was too close, it would be too hot. And if it moved further out, it wouldn't get enough energy from that star and it would be too cold. So either side of that is not ideal. So we've got too hot, too cold, depending on if it's too close or too far away. So habitable is kind of just in the middle, or even known as like the Goldilocks zone as well, because it's just right. Now, the habitable zone does change with star because it relates to the actual output of the star. So it depends how bright the star is, how much energy it's producing, and it then depends on where that planet is in relation to that. So for example, here you've got the sun. The planets and the habitable zone need to be further out to be habitable compared to the star below, which is a red dwarf, which is a very small star, has a very low luminosity or output. So the planets have to be closer basically. So depending on the type of star, that habitable zone will be in different locations, which obviously impacts the planets we're going to find there. So red dwarf stars, as I mentioned, any planets that are habitable around these, which actually interestingly, a lot of the habitable planets we've found so far are around red dwarfs, unfortunately. They're quite small stars. They do suffer from kind of things like quite significant flares as well. But basically, if a planet is orbiting a red dwarf star, it needs to be quite close to that star to be habitable because it just doesn't produce a lot of energy. It's not very luminous. So to get the right temperature on that planet, it's got to be quite close. And then the opposite really, if you've got a really massive star, very hot, luminous star, then the planets need to be much further away to be habitable. Otherwise they're going to be too hot. So they've got to move much further out to basically get the same equilibrium temperature on the actual planet. Now, the interesting bit here is that stars are rarely static in their output. When they're on the main sequence like the sun, they have a long period where there'll be a fairly stable luminosity. It doesn't change that much. However, as they evolve, they move off the main sequence. Some stars do go through a pulsation phase, which means they swell up and then they contract again. They kind of like, they do physically pulsate, get bigger and smaller. Now here, I've given an illustration of that, but it's not technically correct because the colours are wrong. As it swells up, it would actually cool down, so it would kind of go redder. But I've just used a more luminous star and a less luminous red dwarf star just to illustrate that they will get more luminous, less luminous as they kind of pulsate, as they physically get bigger and smaller. So on the HR diagram, if you haven't seen this before, it's basically a scatter plot of the luminosity and surface temperatures of stars, and it creates this sort of plot here, and you have distinct groups of stars on there. The main sequence is where stars are fusing hydrogen in their core, and it's where they spend a lot of their life. As they finish that and evolve, they will move off the main sequence. Now most stars, kind of like the sun and that, they will move to the upper right into red giant phase and then kind of go over and stuff like that. So most stars will move off the main sequence once they finish hydrogen fusion into this section here, and that's typically where we see these pulsation phases of stars as well. So it's once they move off that main sequence into the red giant phase is when they kind of, at least a good proportion of them will experience this variable output and pulsation. Now, hopefully you can kind of see this on your screens. This is kind of like a a video, I suppose, of variable stars in the globular cluster M5. Now, globular clusters don't have any gas in them. They're populated by very old stars, so stars that have moved off the main sequence. And as a result, they have a lot of variable pulsating stars in there. Now, if you look really carefully, hopefully you can see them kind of blinking on and off. If not, I suppose just trust me that is what's happening. And another example here, maybe you can see this one a bit better. These are variable stars in the globular cluster M3, and the zoomed in section is a bit more easier to see. They're a bit slower in their flashing. You can see them get brighter, you can see them get dimmer, and these are typically those stars that are pulsating. They've moved off the main sequence. They're older stars that have evolved into this phase. And one particular type is known as RR Lyra stars. You have things like Cepheid variable. You've got loads of different sorts. And this is an example of what might happen. So they swell up, they get bigger. As they get bigger, their surface area increases, so they get more luminous. They become brighter. Then they contract again, their surface area decreases, they become less luminous. Despite getting hot, their surface temperature might get hotter as they contract, but because they are physically smaller, they're less bright, essentially. And these particular pulsating stars, again, they're occurring just off the main sequence as well. And there's a whole kind of group of those, all different sorts, and the mechanisms that causes the pulsation and variability are all different. And here is a typical light curve for one of those type of stars. So a light curve is just basically the brightness of the star as a function of time. It's done in phase here. Because we know it's a repeating pattern, we can do it over one phase. So from 0 to 1 would be one pulsation. And on the y-axis, you've got the V magnitude, which is essentially the brightness of the star in the visible part of the spectrum. We can see it kind of increasing and decreasing. Now, magnitude, it's actually decreasing, but that's because it's flipped around. It's getting brighter and then dimmer, then brighter, then dimmer. And it will have a repeating pattern. And different sorts of these variable stars will have a slightly different shaped light curve, but they will still all repeat. They still have a repeating pattern. So what's causing this pulsation? Well, this again is just one of the causes I'm going to mention here, but there are a few different reasons as to why they might pulsate. And this one's going to relate to how the actual photons move from the inner part to the outer part of the star. So on the main sequence, they are in hydrostatic equilibrium, which means that the gravitational force trying to collapse it is balanced by the outward radiative pressure from the energy generated in its core. And they're happy just sitting there for a long period of time. They are in equilibrium. They're not swelling up. They're not shrinking or anything like that. However, the way that the photon moves through is going to dictate how this pulsation works. So if you make the star suddenly opaque, that photon struggles to get from the centre where it's basically been produced from the fusion to the outer part, and it stays longer in the atmosphere. That's going to cause the actual star to heat up. So basically, photons will undergo more scattering, more absorption, more interactions when opacity is very high. So it's harder for the photon to move outwards. When it's low, that photon can go through much easier, much faster. Now, when opacity is very high, the movement of the photon is kind of restricted outwards. So as it's moving outwards, it's slowed down. And because of that, the temperature internally of the star increases. Now, as the temperature internally increases, that drives up the pressure. So the star actually expands because we haven't changed the gravitational force. That's not changing. But the pressure has now increased because we've essentially restricted the movement of our photons. So pressure increases, our star is going to now swell up. Now once it reaches its maximum kind of size, I suppose, at the peak of that, it's going to cool down. So there's an increase in radiation emission. The star appears brighter, we're basically measuring more photons, and because of that it cools down. It becomes less opaque, and that is going to cause a cooling of the star. Because of that, the pressure decreases. Again, our gravitational force is the same, but because our pressure has decreased, the star is now going to contract. And what happens is that it goes through a cycle and it keeps repeating basically. It gets stuck in this cycle. So it swells up and then contracts again. And what we actually see when we're looking at a star is we see an increase and then a decrease in its brightness. So we see a spike in the brightness of the star and then it will decrease. And again, this happens for most variable stars. They will have, well, most regular variable stars will have a repeating pattern. There are some irregular ones, but they're not caused by this particular process here. And the time period that this can occur over, it can be it is fast. In astronomical terms, it's days to years, basically. So the star will swell up and shrink back down on the order of days to years. So very, very fast, actually. That's going to cause us problems for our planets when we look at those. So we've now got a planet that is in the habitable zone around a star. That star now becomes a pulsating star. It's moved off the main sequence. And what happens now is it's going to swell up. It becomes more luminous. That causes the habitable zone to move outwards. That planet's still where it was. And again, depending on kind of the configuration here, the planet might stay in the same orbit. It could be disrupted by the bigger atmosphere, but if it's too close, but let's assume that it's not. So that habitable zone, it moves outward. That now means our planet is too hot. The star is more luminous than it was before. The planet gets a lot more energy than it did originally. And then the star basically decreases in luminosity. It cools down, it contracts. Now what's happening here is that habitable zone overshoots the other way. It's going to go inwards, and that's going to mean that our planet actually is too cold. So now our habitable zone is very close to the star. Our planet is sitting outside the outer edge of the zone. It's now too cold. Now what's that going to do to the planet? Well, the planet's going to cycle between extremes in temperature. It's going to be very hot, very cold. And if you remember the period of the pulsation of the star, that can be on the order of days to years. So that's going to really wreak havoc, I suppose, with the planet. If that planet was habitable when the star was on the main sequence, it's now not going to be. Depending on what those extremes in temperatures are and how fast they're occurring, that's going to have significant effects on its climate and its global equilibrium temperature and the dynamics occurring essentially in its atmosphere. So whilst the stars can support a habitable planet, maybe in the main sequence, if it evolves into a variable star pulsation, then it can limit the habitability of that planet. That planet may no longer be habitable. So it's kind of worth thinking about, should we really be looking for planets around pulsating stars? Probably not. That's why we want to kind of look for more like sun-like stars, because we know we're habitable, we're fairly stable to a point. So thank you for watching. If you enjoy the video or find it helpful, then do consider becoming a member. There's extra videos in the members section, but it also helps support the channel. So thank you for watching.